Hello, everyone. Welcome to our live session for, what is this, April 7th. And we are excited to have you. We have a couple of announcements that we want to let everybody know about. We've got a Yuri's Night talk. So I will let you, Chris, talk a little bit about what is Yuri's Night and what are we going to be talking about?
Sure. So Yuri's Night is a worldwide celebration of the first human in space, Yuri Gagarin. And this year it's April 12th, and this year it's the 60th anniversary, so it's a big one. Now since we have a worldwide audience for these Q&A sessions, you will know that this is a really big deal, especially amongst young people. There are parties all around the world. Americans don't quite take it as seriously, I think, because of the intense rivalry we've had with the Russians over the years, including currently. But in Europe, it's huge, and elsewhere in the world, it's huge. So I'm giving a public talk as part of the Steward Observatory Public Evening series at 7:30. That's Pacific time or our Arizona time zone on Monday, which is the 12th of April. And we're going to send a link. It's a Zoom login to everyone that's part of these courses. Also, the following Thursday at 10 a.m. our time, we're going to do a live session that's dedicated just to questions about space travel. So we'll remind people of that. And that essentially will sort of form a Q&A session for the talk, or even if you didn't go to the talk, we just, space travel is a big enough topic that we don't always get questions about, that we're going to have a dedicated single topic Q&A session a week on Thursday.
Excellent. Thank you very much. And I posted the link to the Steward Observatory website where you can find links to the Zoom that will be on Monday, and that's Monday evening here. So it's like 2:30 in the morning Universal time. But we will have that posted up on our YouTube channel, I believe. So we'll post the video after the talk is finished, so that you can catch up if you miss it. Excellent. All right. Well, thank you everybody for joining us. The first question for today is from Wendy Traver, who sent an email, and Wendy would like to know, if the speed of light were not finite, how would that change the universe?
That's an interesting question, a hypothetical. Physicists like these hypothetical questions. The German word for this is Gedankenexperiment, thought experiment, and Einstein was a famous person for doing thought experiments, the sort of what ifs. And they're interesting, they're illustrative because they tell us things about the universe that we might not otherwise have thought of. The speed of light is so fast that it's operationally infinite for practical purposes on the Earth. Light appears to travel instantaneously across a room or across the planet even, and within the solar system. It doesn't take that long to travel. If the speed of light were infinite, it would have a dramatic consequence of our view of the universe, because remember, the finite light speed travel combined with the huge size of the universe and the distances in space mean that we see distant objects as they were when they were younger. And so we have look-back time, the idea that looking out is looking back in time. If the speed of light were infinite, that would not be true. There would be no look-back time. We'd essentially see the entire universe as it is right now, simultaneously, which is a very dramatically different situation than the one we're faced with now. So it's very hard to imagine what that would be like, what astronomy would be like if the speed of light were infinite. It's a problem also because our laws of physics tend to have the speed of light as a physical constant that emerges self-consistently from those laws. And so you can't simply tweak the laws of physics we know to make the speed of light infinite and have them all work the same way. They essentially wouldn't work. So it's one of those hypotheticals that we don't think is physically plausible.
The next question is from a live participant. Tyanis Kuto asks, if there is a multiverse, could the universes that exist and arise within it start as quantum fluctuations in a high dimensional space? So that's pretty specific. Could you just talk about how that could work?
Sure. The multiverse concept arises from what astronomers loosely call quantum genesis, the idea that our space-time, our visible universe, emerged as a quantum fluctuation. And indeed, if you trace the Big Bang backwards far enough to the convergence of all the four forces, you are in a situation of quantum scale. And so it's a plausible scenario. The extension of that to imagine there are other quantum fluctuations is one level of hypothetical cosmology that is not supported by data at the moment. It's just a plausible speculation. The second level of speculation embedded in the question is the idea of multidimensional spacetimes, and these emerge out of string theory. String theory is one possible theory, an overarching theory that would explain the unification of the four forces, which we do believe occurred at the instant of the Big Bang. And in that theory, the theory is only self-consistent in spacetimes that have 9 or 10 dimensions of space along with the one of time. And so these higher dimensional spacetimes, we have to explain why they're not apparent in our universe if they were there at the beginning. And the explanation is essentially that they're compactified or only accessible on incredibly small scales or at incredibly high energies. So the specific expression of the multiverse idea through string theory does indeed allow for the possibility of other spacetimes in hidden dimensions. And that the behaviors of the spacetimes that in the 3 dimensions we might see are concealing invisible behaviors that occur in dimensions not accessible to us directly.
The next question is from Predrag Ivosev, who asks an interesting question via email. Is it theoretically possible to reconstruct images from light bounced back from the Earth, such that a sufficiently distant civilization could watch humans build pyramids, or further back watch dinosaurs roaming the Earth?
Yeah, this is an interesting idea. I've seen several articles about this over the years. It's hypothetical. I mean, the technology to actually retrieve such images from far away planets or to use a mirror over such distances does not exist. We simply cannot resolve the scales small enough to make images of distant planets and therefore follow light. But in principle, if what you can imagine, of course, is that some distant civilization with the ability to have telescopes and focus light could also erect huge mirrors in space. And if they pointed such a mirror at us, then indeed that mirror would be reflecting light from us. And so imagine that place where the mirror has been erected is a star and a planet that's 1,000 light years away. That would be 2,000-year light travel time. And so looking into that mirror, we'd see the Earth as it was 2,000 years ago, around the time of Christ. And a sufficiently far away civilization pointing a mirror at us would illuminate for us the time of the Egyptians or even further periods of time. So it's a very interesting concept of requiring extreme intelligence of a civilization and capabilities for them to erect such a mirror, and of course capabilities on our part to actually gather the light from so far away with sufficient resolution, which we simply don't have at the moment. So it's a very much a hypothetical question.
The next question is from Wiedmond, who asks, I'm wondering if there is anything new regarding hypervelocity stars and if any new ones have been discovered.
Yes, every few months there's a publication or a preprint about hypervelocity stars. Hypervelocity stars are stars in the Milky Way galaxy whose instantaneous velocity, measured either by a combination of the Doppler shift and sometimes by their proper motion or apparent motion on the sky, which is a transverse speed, have velocities that far exceed the binding speed of an object in the galaxy. Essentially, any star with velocity much more than 300 or 400 kilometers per second is not going to be bound into the disk or the halo of the galaxy. And there are stars with velocities much larger than that, with thousands of kilometers per second. And so these stars are clearly not bound to the galaxy. They are probably given these high velocities by kicks in binary or multiple star situations where you use a sort of extreme gravitational slingshot mechanism to give one member of a small set of stars a very high impulse, which is sufficient to leave the system. We've also seen stars that are essentially in intergalactic space. So these are hypervelocity stars that have indeed already left the galaxy, and we've seen others that have high enough speed that we know they're going to leave. So the interesting thing for astronomers with hypervelocity stars is not their existence, but the mechanism by which they get such high velocities. And those are interesting interactions, and sometimes they're interactions in very tight binaries or involving compact objects like neutron stars or pulsars. And so there's some pretty extreme astrophysics involved in creating a hypervelocity star, and that's what makes them interesting.
The next question is from Lawrence 4040, who's on with us live. Can you explain why redshifted light does not violate conservation laws?
Okay, that's a good question. First of all, what do we mean by redshifted light? In the sense of cosmology, the redshift is caused by the expansion of space-time, the expansion of the universe, and so we call it a cosmological redshift. So you have to consider the dynamics or the behavior of the entire universe to decide whether there's a conservation of energy principle being violated or how it applies. So what that means is that as space-time expands, photons have their wavelength actually stretched by the expansion. So in that sense, yes, the photon is losing energy as it travels through expanding space-time. And you might say, well, where is the energy gone? Well, the energy, of course, has gone into the expansion. So the expanding universe has a sort of gravitational potential energy from all the stuff in it, and it has a kinetic energy from the motion of all objects within it. And so there is conservation of energy in that sense, that the loss of energy of the photon is balanced by the extra energy the universe has in its expansion, which is an outward expansion.
And then as a follow-up, can you talk about how redshifted light affects dark energy or is affected by dark energy?
So the relationship between redshifted light or light traveling through the universe and dark energy is not entirely clear. Light traveling through the universe is subject to the cosmological redshift due to the expansion of space-time. That's just a part of standard cosmology. Dark energy is an entity, a sort of force, if you like, that emerges from the vacuum of space. And it has a constant strength as the universe evolves and as space-time expands. And that essentially is what drives the accelerating expansion. So in a sort of energy and mechanical sense, the two things are not really related. Photons are traveling through space-time, and dark energy is an agent to cause the accelerating expansion of space-time, regardless of whether that space-time contains photons or particles or whatever it contains. So there does not seem to be a direct relationship between dark energy and the nature of the redshift of light.
Excellent. The next question is from Barbara Fives. How do planets form their magnetic fields?
It's an interesting question how planets form their magnetic fields, and also what magnetic fields different types of planets have. Small objects in the solar system essentially do not have magnetic fields. Asteroids don't have magnetic fields. Small moons do not have magnetic fields, but some do. And small planets do not have magnetic fields. So Mars is famous for having a very weak, if absent, magnetic field. Magnetic fields in planets are associated with their metallic cores. So the cores of planets like the Earth, for example, and Venus, and the gas giants, although we can't directly see their cores, are likely to have metallic cores. And the magnetic field entrained in those metallic cores is held there, is essentially trapped by the metallic medium. The question of where that magnetic field came from is that it must have been present in the material that formed the planet, just as the sun's magnetic field must represent the amplified version of a primordial or original magnetic field that threaded the interstellar cloud that led to the sun. So there are magnetic fields in the universe. There are dynamo mechanisms in swirling gas clouds and plasma clouds that generate small seed magnetic fields. So the mechanism is there to generate a seed magnetic field at a modest level. And so in a large nebulous cloud, when that cloud collapses, if the magnetic field is entrained in the plasma, then that magnetic field will be compressed as the cloud collapses, and so will strengthen. And so within the solar nebula, that compression and collapse strengthens the magnetic field that now threads the sun. And within the regions where planets form, it's the same idea. There's a small seed magnetic field that gets amplified and compressed and then trapped or retained within the rocky metallic core of the planet. and planets not big enough to have a rocky metallic core are likely to have a zero or very, very small magnetic field.
Thank you very much. The next question is from Isla, who sent an email. If the cosmic microwave background is a result of an event with a beginning and end before our time, will we stop seeing it in time when this envelope has passed us, or is expansion stretching it so that it will never pass us?
It's never going to pass us. The microwave radiation is a signature of a phase after the Big Bang that occurred after about 400,000 years, actually about 380,000 years after the Big Bang, when the temperature of the universe cooled enough that stable atoms could form. And so two physically related things happened. One was called recombination. That's the combination of electrons with protons to make neutral atoms for the first time as the universe cooled. And the second was decoupling, which is when the electrons became attached to the protons, they stopped scattering photons. And so the universe became transparent, having been opaque before that. So what we see when we look at the microwave background is a representation of the universe, the entire universe at that time when decoupling happened, 380,000 years after the Big Bang. We see it in every direction because this physical event occurred in all space-time. And therefore, since it's an image, since the microwaves themselves, whenever we see them, are an image of that event, that doesn't change as time passes. The only thing that does change is the expansion of space-time stretches those microwaves out to lower and lower energies and longer wavelengths. So in the future, the microwave background will still represent an image, if we can observe it with radio telescopes, of an event for the entire universe 400,000 years after the Big Bang, but the radiation from that event will have spread through expanding space-time and been diluted by that expansion and stretched by that expansion to be longer and longer wavelength radio waves.
The next question is also from an email. If the recent discovery of the differential rate of the decay of, I'm sorry, I lost the name of it, B mesons, I believe, I guess B meson decay, holds, if that holds up, what would the implications be for the standard model and for physics in general?
Yes, there's a result that's bubbling at CERN, which involves a B meson factory, as they call it at CERN. It's an experiment on the Large Hadron Collider, a very spectacular experiment that's looking at a B meson decay path. And it's found an asymmetry in the decay path between two modes, which indicates an asymmetry between matter and antimatter, for example. It's an asymmetry that was not anticipated in the standard model of particle physics. There were supposed to be equal decays in the two channels, and they're not equal. It's important first to point out that the significance of the event is slightly more than 3 sigma. I think it's 3.1 sigma. And in normal statistics and Poisson or Gaussian probability, the odds of that happening by chance are indeed 99.9%. That's not going to happen by chance, so it seems a real result. However, in high-energy physics, subtleties of how we count events and backgrounds and so on mean that they're very conservative. So high-energy physicists will not publish or can claim it as a real effect until it's 5 sigma. And at that level, the odds of it being wrong are about 1 in 100,000. For example, the Higgs particle, the Higgs boson, was not claimed as a true detection until it reached 5 sigma. So this B meson asymmetry is not in the legitimate detected category, and people are just quoting it as a tentative result. If it is a real result, however, it'll be probably one of the first extensions, or require one of the first extensions to the standard model that's occurred for a long time. And so it's very exciting. I think theorists are still trying to work out the implications of this result if it holds up.
The next question is from Shakir61. Can humans ever make it outside of the Milky Way galaxy?
I don't think we'll ever make it outside the Milky Way galaxy until and unless we develop the technology of suspended animation. So humans obviously have finite lifespan. The only 2 ways we could ever make it out of the galaxy were by traveling at essentially light speed, so that time dilation would kick in and we could age a tiny fraction of the time it might otherwise take to get there. But the energy costs of humans traveling at light speed are essentially prohibitive, so that's not going to happen. The only conceivable way it could happen is if we perfect the idea of suspended animation, suspending humans' biological processes, putting them essentially in the deep freeze and then reanimating them. And then the travel speed could be more modest, maybe 1% of the speed of light. To leave the galaxy is 100,000 light years across, and we're, well, a third the way out of one side. The easiest way to leave the galaxy is to go up or down out of the disk, and then the distance you need to travel is more like 1,000 light years. Well, 1,000 light years at 1% of the speed of light is 100,000 years, so you'd have to be able to put humans on ice or suspend their life processes for 100,000 years and then reliably reanimate them. Of course, the question is, where would you go? Once you've left the galaxy, there are no stars and there are no planets, there are no habitable places. So this is not a very friendly place for humans to ever go.
The next question is from EJ Wilrich, or sorry, DJ Wilrich, no, sorry, EJ Wilrich. Can you succinctly describe the information paradox with regards to black holes?
Yes, the black hole information paradox arises from a disconnect between the general relativity theory that says that an event horizon is an impermeable barrier to information, and a principle of quantum theory, very well tested theory of physics, that said that information is preserved in particle interactions, and particle interactions can flow forward or backward in time. And so the paradox or the problem arises at the event horizon when fundamental particles are, say, interacting near the event horizon or into the event horizon, and physics says that you should be able to reverse that interaction or that exchange and recapture the information, but black hole theory says that that information is lost forever. So there's a conflict, a fundamental conflict there between relativity as expressed in an event horizon and quantum theory as expressed in the reversibility of particle interactions. And that's a pretty profound problem. It's led to probably hundreds of research papers since the 1980s. And there are various ways to try and escape this paradox. One involves the idea that information is not completely lost when it falls into a black hole, but as particles or matter falls asymptotically onto the event horizon and as time slows down, that information is somehow encoded onto the event horizon in a sort of holographic sense. That's the holographic principle. So the holographic principle was developed to get out of the information paradox. And there are other theoretical ideas out there, but at the moment the paradox is not fully resolved. It's still a problem.
Excellent. The next question is from one of our live participants. Parzival Fusto asks, previous research from the University of Copenhagen suggests a new model of the universe that casts doubt on the possibility of 70% of our universe being dark energy and that it may not exist. Are you familiar with this model, or are you familiar with this work? Can you comment on that?
Yes, I think this is the idea that's been in the preprints and the news lately. It's the idea that you can do away with the need for dark energy if you attribute a particular property to dark matter. And you may mean you need two forms of dark matter. So, and it actually involves some magnetic forces. So we know very little about dark matter, unfortunately. But this is a clever idea. It's trying to use something we don't know much about, but are on a close chase for, dark matter, to obviate the need for this strange entity, dark energy, that we really don't understand at all. Reaction to this idea in this paper has been mixed. I would say some people think it's a creative way of getting out of needing dark energy, since we really don't understand what it is and it doesn't fit into fundamental physics. Other people decide that this is, while clever, it's a little ad hoc, and there's no particular reason to give dark matter such strange attributes that it has the implication of expanding space-time at an accelerating rate. So I would say it's an interesting theoretical idea. There's certainly no evidence that points in favor of it as opposed to other explanations. So it's just part of the ferment, if you like, in the theoretical community about the things we don't understand, dark energy and dark matter.
The next question is from Serkori. How does omega lambda, or the amount of dark energy, vary from the time of the Big Bang until present day?
In principle, if dark energy has the attribute of Einstein's cosmological constant, then it is literally was a constant of integration in the solution to the field equations of general relativity. And so that means it's literally a constant over time and across all space. And so the dark energy was an ingredient built into the Big Bang. It's an initial condition, if you like. And as space-time has expanded, the absolute strength of that quantity, that lambda, has not changed. And that indeed is what drives an accelerating expansion. So as more space is created, the amount of dark energy in any volume of space increases or stays constant, which means the total amount of dark energy in the universe is increasing, which drives an accelerating expansion. So it's really built into the foundation of the Big Bang itself.
The next question is from an email, and it's been discussed in the chat as well. Do you think something like the Alcubierre warp drive or something similar like that is possible or could be achievable within the next 100 years or so?
Well, this is a controversial topic. The Alcubierre, don't know how to pronounce it exactly, warp drive, an idea that came a decade or more ago. I don't remember when the first paper was written. It's a sort of exotic electromagnetic mechanism for creating a sort of wake warp drive, which just creates an enormous amount of acceleration and in principle gets you to light speed and beyond. Physicists are, in large part skeptical about this because fundamentally it is violating certain laws of physics, the one from special relativity that the speed of light is an absolute limit. Now, physics does allow for hypothetical particles called tachyons, which only exist in the faster than light domain, and they have essentially a shadow set of quantum properties that allow them to begin at light speed and then accelerate beyond that. But there's no evidence for tachyons, so it's very hypothetical, and you cannot create any energy mechanism or practical technology from something hypothetical like that. And the Alcubierre warp drive is in the same category. The physics it's based on does violate some core precept of relativity, and it's a technology that we're nowhere close to being able to even try out to see if it worked.
One of our live participants would like to know, can humans, or do you think humans will ever build something that can overtake our most distant probes like Voyager 2, given the technology improvement over the years?
Absolutely. So the Voyagers and the Pioneers, the four spacecraft that have essentially left the solar system, they were launched in the 70s, and they've been traveling at fairly high speed to escape the solar system, and they have the advantage of decades of time doing it. It's clearly possible for us with current technology to exceed those speeds. And the way we would do that is with smaller spacecraft and solar sail technology. So with solar sails provide an impulse from radiation pressure from the sun, the star, and it's a slow, steady impulse. So it's good for accelerating a probe modestly but consistently over a long period of time. The limitation, of course, comes as you get further out in the solar system. The impulse reduces with the inverse square of distance because the light diminishes. So you'd have to get your acceleration in the first few 100 million miles away from the Earth. But we have technology already that for a small probe and a solar sail, maybe a few 100 square meter solar sail, would definitely be able to catch up with the Voyagers and the Pioneers if we wanted to.
The next question is, does the universe need dark matter to form galaxies?
Yes, at the moment, our understanding of galaxy formation is very much predicated on dark matter, which is to say every galaxy we've studied so far, including the Milky Way, is embedded in a halo of dark matter. That dark matter outweighs the normal stuff by a factor of about 6. And without that dark matter, the galaxy would not hold together. It would not be bound. It would literally fly apart with the cosmic expansion. So reversing that, the corollary is that yes, dark matter mediates galaxy formation. It's essential for galaxy formation. And the way to think of this is that as the dominant mass component of the universe, as the universe expanded and cooled in the first few 100 million years, the puddles or wells of dark matter gradually became stronger and stronger, because dark matter exerts gravity, even though it doesn't interact with light. And these potential wells of dark matter gradually increased over time, and then eventually baryons or normal matter flowed to the center of these wells, and that normal matter interacted, because it does emit light and radiation and interact with radiation, and stars could form, gas clouds could collapse. And so you have a scenario which computer simulations are pretty good at showing is plausible, where slow clustering of dark matter alone in the universe before galaxies formed sets the stage and provides the seeds for galaxies to form, and then eventually the visible parts of the galaxies collect in the center of those potential wells. So good dark matter is absolutely fundamental to galaxy formation and the properties we observe them to have today.
Barbara, who's on with us live, would like to know if there are colors in space.
Yes, there's light in space, and so there are colors in space. When we see the color of stars in the night sky, those are colors that reflect the temperatures of their photospheres. They're muted. Most planetary images you see in the solar system from NASA have their colors amplified, which is a little misleading. So the colors are muted, but objects in the solar system also have colors. So anywhere there is light, and light has a wavelength, we can imagine things having colors. So planets have colors, small rocky objects have colors, stars have colors, galaxies are collections of stars, so they have colors, and there are colors throughout the universe.
The next question is from one of our live participants. Eldon asks, is there any possibility that Mars can host life?
There certainly is a possibility, because under the surface of Mars, we are almost certain that there is liquid water right now, that it exists right now, that we could somehow visit and see, and then we'd look for life in these subsurface aquifers. So the surface of Mars is sterile, is baked, is cold, is a desert, is blasted by ultraviolet radiation and cosmic rays, almost certainly sterilized, and down into the soil or the regolith by a few centimeters as well. But down below, kept liquid, even in this cold environment, by pressure from the rock above and radioactive heating from below, there seems to be liquid water, and there's just increasing evidence from radar and from even direct observation of aquifers spouting runoff down valleys on Mars episodically, that there's liquid water under the surface of Mars. So anywhere there's liquid water, carbon-rich material, and a local energy source, there could be biology. And so that's why we think there could be life on Mars right now.
So there's some very exciting technology on Mars right now. The helicopter Ingenuity is going to fly soon. Can you talk a little bit about that mission and what's the purpose of flying a helicopter like that on on Mars?
Yeah, the helicopter technology is nice. It's almost like a drone technology rather than thinking of a helicopter. It's a pretty small object, more like the size of a drone. Prototyping this technology is really important. It's one of the huge innovations of this rover compared to the Curiosity rover, which is essentially the same design, the same hardware. So they packed a lot into the Perseverance rover. The helicopter technology is important for two reasons. First, it's just a proof of concept that you can travel around Mars with your probes other than as a rover does, because the rovers are limited. The rovers are limited in their distance. They wear out their moving parts. They have hazards they have to deal with, which, as we know, one of the twin rovers, the small rovers, got stuck in a sandbank and essentially couldn't extricate itself. They could tip over. All sorts of things could happen to the rovers. And so it's a different mode of traveling, and it gives you more range in principle because you're not bounded by the geography or the topography of Mars. You could go into a deep valley, you could go to a high mountaintop, you could go into a very difficult place. So they're important for that. They give added range to exploration. They're also prototyping a technology that is planned to use on Titan. So there's a mission planned for Titan, a moon of Saturn, which has a quite thick atmosphere, actually, much thicker than Mars. And so we're pioneering drone technology for use in other situations in the solar system. Now, the challenge of the drone and why it's going to be spectacular to see it work is that testing these drones is really difficult. Remember, Mars has less gravity, 40% of the gravity of the Earth, and a very, very thin atmosphere. So when this helicopter was tested on the Earth in the lab at JPL, it had to be tested with a very clever, obviously in an evacuated chamber to simulate the lack of atmosphere, and also with a very complicated tether counterweight system to give it the appearance of less weight or mass than it really would have on Mars. And that was really challenging to do test flights in that kind of situation. They did a good job, and they are pretty confident that it's going to fly as they hope it would, but they can never do a full test of its flight on Earth the way it will be on Mars. So there's always a little uncertainty about how it will perform.
Jolly88 would like to know if you can talk about, I guess, Stephen Hawking's research and what has he ever talked about time travel, and what do we currently think in physics and astronomy about time travel?
Stephen Hawking, was a very accomplished physicist and astrophysicist, and he wrote about a lot of subjects. He wrote a fundamental book on the nature of space-time early in his career with Roger Penrose. It's foundational work. He obviously did large contributions to black hole theory. So his contributions to cosmology and black holes were enormous. I don't know that Hawking ever wrote in a technical article, that is a peer-reviewed proper journal article, about time travel. I don't believe that he thought that that was a possibility, because he understood the limitations of the laws of physics. So as far as I know, he did write about our future. He wrote about the human future, the need for us to escape eventually our planet, or have the ability to live elsewhere in case our future was not here, because it was impossible to keep the Earth maintainable. So he was very much in favor of space travel and of doing that in an aggressive way. But I think he recognized that time travel was something that physics laws did not allow.
Ananya Desai 24 asks, can you please explain general relativity theory and maybe talk about how it's different than special relativity?
Sure. In a short answer, I'll do this at a very high level. General and special relativity are two of the foundational theories of modern physics, emerging from the early 20th century, from the hands of Albert Einstein primarily, but also involving other physicists. Special relativity is the theory that deals with motion in what are called inertial frames, that is, frames of reference on the Earth or in the lab or anywhere else, where we can synchronize clocks and talk about travel from one place to another. And special relativity takes as a premise that the speed of light is constant and independent of the observer. And so this was based on the Michelson-Morley experiment, which showed that the speed of light did not depend on the motion of the observer as the Earth moved around the sun. And the implication of the constancy of the speed of light is that space and time have to be supple. They have to be dilated or altered as speeds approach the speed of light. So that's the special theory of relativity. The general theory of relativity generalized this to talk about any force that could cause a change in motion. So you have acceleration, and special relativity says you can never accelerate to the speed of light, but it doesn't talk about the nature of the acceleration. General relativity is talking about any type of acceleration at all, any change in motion, and it's removing the distinction between an acceleration caused by gravity and an acceleration caused by any other force. That's the nature of the general part of general relativity. And as a theory of gravity, it has the extraordinary implication, when working through the math and the conceptual part, that space-time has to be curved. That's the only way to account for this theory. So these are the very broad brushstrokes of special and general relativity, and they emerged from Albert Einstein. General relativity is a masterwork of physics, of course. It was an enormous amount of effort It's been bolstered, and both of these theories are proven over and over again in physics labs around the world thousands of times a day. Well, general relativity is tested not quite as often, but it's also passed every test.
Excellent. The next question is from one of our live participants who asks, let's see, they ask if Pluto exists or not, but perhaps we can talk about what we know about Pluto and the history of its discovery and why it's not considered a planet anymore.
Right. Pluto was for a while the 9th planet in the solar system for some period of time, actually, for half a century. It was discovered by Clyde Tombaugh, working at the Lowell Observatory in 1930. And Tombaugh, as other astronomers at the time, were looking for a further out planet than Neptune. I remember Uranus was discovered by William Herschel, and unexplained motions or deviations in Uranus from an expected orbit led to the implication of an outer planet called Neptune. And Neptune was essentially discovered based on that discrepancy. Well, Neptune and Uranus each have their own variations or perturbations that are not explained by those two objects. And so the hunt was on for a yet more distant object, and that became Pluto. However, Pluto, having spent some time as a planet, was demoted essentially for 3 reasons. First of all, the properties of Pluto are that it is on a highly inclined orbit compared to the ecliptic or the orbital plane of the other planets. It's a highly eccentric orbit, and it's a very small object. It's smaller than Mercury or the Earth, so it's by far the smallest planet in the solar system. So those 3 facts led to a hypothesis, we'll never know for sure, that Pluto is a captured object from the distant region beyond Uranus and Neptune. It's called the Kuiper Belt. The region between 30 and 100 astronomical units is full of icy rocks of various sizes, including some that are almost as big as Pluto, one that is as big as Pluto. So Pluto seems to have been captured, and so it didn't form in its place as a legitimate planet. It's small enough that there are other objects of its size and perhaps bigger in the outer regions of the solar system. So if it were a planet, you'd probably have to add a couple of other further out planets once they're discovered. And it's not big enough to have evacuated a zone in the early solar system, which is the 3rd criteria that the astronomers use for the definition of a planet. So it got put into a new category called a dwarf planet in 1995.
Aldan, who's on with us live, would like to know if it is possible that life from other planets has come to Earth.
It's an interesting idea, and of course there are a number of people, and I've met them, they ask me questions at many of my talks, who believe this has happened and that this is what UFOs are, and that aliens have indeed visited the Earth. I'm not persuaded by the evidence. I realize some of the evidence is quite intriguing. The videos that have been released, some from the military and so on, and they're not that easy to explain, plus many eyewitness accounts. So at the moment, the jury is out, I would say, among most scientists. So they would not credit the fact that there is strong evidence that aliens or anyone has already visited the Earth. Whether or not this has happened in the distant past is much harder to tell. So I don't believe it's happened in human history or in modern times. As for much longer time scales, that's actually harder to tell, because if alien civilizations existed and were exploring the galaxy and had visited the Earth hundreds of millions or even billions of years ago, there's very little way we would know about it. Remember, the Earth has been transformed since earlier epochs. The surface of the Earth has been terraformed or overwritten by lava and weathering and erosion dozens of times since the Earth formed. So any physical traces, unless there were huge artifacts, would have been lost. So it's really hard to rule out alien visitations in the very distant past. But again, you'd have to have something that you couldn't explain that would point you towards that hypothesis before it became a reasonable hypothesis.
Shakir, who's on with us live, would like to know, what are the clues that NASA looks for when looking for life and observing purely from a distance, like from the Earth?
So the clues that NASA looks for in its missions and telescopes, its space missions and its telescopes for life, are that the fundamental one that astronomers are using with telescopes is a global alteration of a planetary atmosphere by biology. The telltale sign of life on the Earth, if you looked at the Earth from far away, is the oxygen in the atmosphere. Because if the biosphere shut down overnight, imaginary experiment, it's not going to happen, that oxygen would disappear quite rapidly. That oxygen is produced by respiration and is produced by biology. Most of that oxygen was created by microbes a few billion years ago. And if there were no restoration of that oxygen would dissolve into seawater, it would rust things and oxidize things and would disappear. So a non-biological planet does not have a large amount of oxygen in its atmosphere, and our planet does. So that's probably the biggest telltale of life. And these telltales are called biomarkers by astronomers. Biologists have their own use for that term, but astronomers use that term to refer to life, evidence of life beyond the Earth. That's the main one. Other ones involve other gases that are part of biology. Methane is a life-associated gas. And so that one, as we've seen, phosphine, very argumentatively, was possibly implicated in Venus as something associated with life. So gases in an atmosphere that indicate biology are the primary tools that NASA will look for life. The other evidence, of course, will be physical evidence. If we get to Mars and we actually see fossilized evidence or tracers of microbial colonies, which are called stromatolites on the Earth, then that would be even more direct evidence, fossilized life forms or trace fossils, the remnants of colonies of microbes from early in life's history. That would be more dramatic evidence. And of course, the most dramatic of evidence of all would be a technological artifact that we couldn't explain any other way.
So just speculating here, folks are discussing if life does exist elsewhere, what are the possibilities that it looks like us? What are the chances that it would have the same kind of physical form factor?
Yeah, there's a lot of argument about this, and I would say astronomers, biologists, the scientists who think about this, they definitely don't agree. There's one argument based on looking at the history of life on Earth for what's called convergent evolution, that to solve the problems of surviving in an environment, life or biology makes similar solutions. And examples of that might be the eye. So mammals and primates have an eye, but cephalopods have an eye. Octopuses diverged on the tree of life from us 400 million years ago, and they have eyes too. They're actually better than our eyes. They don't have a blind spot. So life has developed eyes on different strands of the tree of life. And there are other attributes of life that form commonly despite having different origination paths. This is the convergent argument, and this would lead to the fact that we might expect, say, brains or eyes or limbs for locomotion in other situations of life. There's a countervailing idea that we don't really have good enough evidence to be sure of that life evolves in a physical environment. If the physical environment were totally different, life might be very different. So when we're thinking out of the box about life and we're acknowledging that habitability can occur in situations that are really quite different from the Earth, then we might imagine that the biology that emerges from those situations might be quite different and might even be unrecognizable. That's a possibility. It's very hard to talk about it until we go beyond the hypothetical and have some other examples to look at.
The next question is from Oxbowman, who poses the question, let's assume that simple bacteria are found on Mars. What do you think will be the societal consequences here on Earth? Would it be a quick blip of news reporting and return to the status quo and sort of a big shrug at the end?
I think it'll be somewhere in the middle. It's a good question because it could well happen. I think it will obviously be front page news and headlines for several weeks. It'll be a huge discovery and a foundational discovery. But because it's a microbial form of life, not an alien that we can talk to, the broader public will probably lose interest at some point. However, I think science will be changed forever by this. Biology will be changed forever. For the first time, biologists have only ever been studying life on Earth. We'll have a second example to study, and it'll either be like our form of biology or different. Either way, it's important. And so biology will be changed forever. Astronomy will be changed forever because having found a second example in one solar system, the odds of life being formed elsewhere in habitable worlds that we're finding by the hundreds goes up dramatically. And so the game will be on for finding life elsewhere in the universe. So I think science will be transformed for more than just a few weeks or a few months, but forever. And the general public will be very excited, and it'll come in and out of the news for a few months, and then people will go back to doing their normal business.
All right. The next question from one of our live participants is from, let's see, Aisha Luman. I'm sorry, I probably butchered that name. Is there only one sun, or does every planet have its own sun?
Well, that's an interesting question because we used to think that every planet had its own sun, that planets form as a byproduct of star formation. Remember, if you swept up all the planets and all the other stuff like asteroids and comets together in the solar system, it's less than 0.1% of the sun's mass. So planets really form from the residue, what's left over, the sort of metal-rich and heavy element-rich outer parts of a solar nebula as it collapses. So we think it's therefore a consequence of an existence of a planet that it must have a star, because the star formed from most of the material. The exception to this, of course, is interesting, and that's the fact that we do believe, and we've detected a few, that there are what are called rogue planets. A rogue planet is a planet that early in the formation history of the solar system was ejected from that solar system due to one of the violent interactions that happen in the early days of a solar system when the planets are being built. There's definitely a substantial chance that a terrestrial planet, say in the inner solar system soon after its form, will either suffer a collision or an interaction sufficient to kick one of those planets out of the solar system. At that point, it's floating through interstellar space, and it has no star. In some simulations, there are almost as many rogue planets as normal terrestrial planets. But even if it's only a fraction of them, that's a huge number of planets floating around in interstellar space. Because they don't have a parent star, it's very hard to detect them. And we found them essentially just by the microlensing method. But that's a clear counterexample where a planet does not need to have a star.
All right. We have a couple of events that we various staff members have to get to today, so we're going to have to wrap up a little bit early. We have time for one final question, and we will take this one from Maisie 211, and then we will wrap up for today. For those of you who are interested in the live stream next week and the Yuri's Night presentation, I put the URL in the chat window, and then we will also send that out as an announcement through our Coursera and Udemy listservs. So the question is, if life is found somewhere else in our solar system, isn't it more likely to be cross-contamination rather than a second genesis?
That depends where it's found. It certainly could be cross-contamination. The ability for life, biology, to travel through the solar system very much depends on where it's going. First of all, the biology would have to be protected in a rock, well within a rock, and not exposed to the vacuum of space or UV radiation. It also depends on the probability that that rock could travel between planets. The sort of very inefficient conveyor belt that moves rocks in and out of the solar system works more efficiently in the inward direction than the outward direction, for the obvious reason that the sun is the big source of gravity. So it is therefore easier for a rock to get from Mars to the Earth than the other way around. Doubly so because Mars has weaker gravity, and it's easier for a rock to be blasted off Mars and go into space than it is for a rock to be blasted off the Earth and get through this thick atmosphere and through the heavier gravity. So that's an example where it is much easier for a rock to get from Mars to the Earth than the other way around. It's also similarly hard for a rock to get off Venus and travel out into the solar system to us or to Mars or further out, because Venus has an even thicker atmosphere and as much gravity as the Earth, and you're going against the sun's gravity. So not all transits are possible within the solar system. And then for the outer solar system, the vastness of the space between planets means the odds of a rock actually making it from a planet or a moon to another destination become incredibly small. And so most scientists, planetary scientists, think that that essentially has not happened in the outer solar system ever or at all. It's a good question to end with. Thanks very much for participating, and we have a special week next week with a single topic Q&A session a week on Thursday, and my public talk if you can make it. I know it's a hard time for some people because it's the evening in Arizona at 7:30 on Monday, Yuri's night.